Thank you and good afternoon. Very pleased to give a presentation on OS streaming powered by CMCD. Yeah, I hope that you enjoy the event as much as I do. I think it's very high quality, so I'm very pleased to be here in a good company. So today my agenda is going to be to give just to fly over the state of the art of OTT video delivery and what the challenges are. So I picked two. Obviously there are more challenges. We heard a lot of this morning. I'll just fly also over CMCD, just give a quick recap because many of you probably already are aware about what CMCD is about. And introduce then the audience OS streaming concept. That's how we call it, where we do all these optimizations, efficient delivery. And then I give two groups of applications. One is about CPU encoding optimization, and the other one is about ladder and representation optimization. There's a lot of applications, so we're going to show that. So in first place, what's the state of the art in OTT? You have a problem that you want to optimize. You want to offer the best user quality of experience, but you have also processing encoding costs that you want to ensure to be as low as possible, and that's also for us, basically what we deliver. And you've got the delivery costs also, the CDN costs. Now, how do? You generally, for encoding, this is a long-time experienced engineer sometimes which is doing this based on long-term analytics, or you have some guidelines, whatever ladder, whatever codec profiles you use, whatever codecs you want to use, segments, and so on, so optimization. But that's rather long-term experience, knowledge, know-how. So you have static profiles, basically. On the delivery cost, what you do in order to avoid any frustration whenever you have, for instance, for sports events, you just oversize your CDN to be sure that it's going to fit for the peaks, at least for the given program. Okay, then there comes the question, of course, do you have the best quality of experience for the money? I'm not sure. There's at least something which can be done on this. So next, I wanted to next, I wanted to also talk about one particular problem, which also is very close to my daily job, basically. It's about the new codecs. So there's always a question as an engineer or also as a platform operator, when do you introduce new codecs? Of course, on the good side, you've got lower CDN delivery costs because, of course, codecs are more efficient. That's at least what you want to see. You've got a better quality of service. You got better audiovisual quality of experience for HDR, for UHD, for instance. That's at least what you can offer. You show technology leadership. I'm the first who has these new codec. And you can offer also, amongst others, better mobile experience, where especially you have some congestions in the mobile network. But on the downside, you've got a strong legacy on the install base, which H.264 is. I mean, today, I think it's more than 70%, which is still streaming H.264. But HEVC is out already since 2013. And we have VVC as the next generation, talking also about AV1. And then I'm just saying that, of course, we're also guilty of something. We continue to improve the legacy codecs. So we don't just say, okay, this is over, we don't continue. And that's also very attractive to continue to keep on using the same codecs. And basically, that's the truth. I mean, for the encoding, the most money we make out of the legacy codecs, not where the new codecs are. And then the new question which comes up now is which codec to use. I mean, you heard probably of the codec war. There are several terms of that. So AV1 and VVC, potentially, and HEVC are the three ones that you might want to contemplate. You could add also to that IVS3, which is more for Asia or Chinese, and LCVC could be also one on top of that. But basically, it's between AV1 and VVC. So that's also given some insecurity. And then, of course, new codecs are complex as well. So that means that where you could fit in on a bare metal maybe a couple of X channels in H.264, you can do less in HEVC, and you can do even less for VVC in AV1. And that means that it's reflecting on the price for the encoding costs. So that's the kind of questions that you might want to ask yourself. And again, if you have to take a decision from now on, I'm going to start to encode in this codec, well, this is long-term pricing, long-term investment. CMCD, I just wanted to fly over to explain a bit what it's all about. Many of you probably know. It's a standard delivered by CTA. It's 5004. It's about analytics, basically. So it's a common media client data, and it allows basically to retrieve some information and to report this, so amongst others, to a CDN. And you have four different features or group of features, which I identified here as the buffer starvation flag, so that helps immediate recovery for if there is any issue with the buffer on the run. Prefetch hints lets you basically to prefetch to tell you what to cache basically at the edge already in terms of segments. Session identification is very important. That helps when you do the analytics, instead of having just the random, okay, this IP address requests this kind of segments, but you don't know where this belongs to. This helps you to know who has a session, which user is using a session, which device, and what segments is called, and so on. So to gather this into one session. And then you've got these features like bitrate, buffer, and segment signaling, which also are very helpful to allow the CDN to optimize the migress. So in a nutshell, it's just data to optimize. It's a very simple mechanism. You can also enhance also so in a private way these data flags, but it's a standard, so that's very important, and the adaptation rate is also very high of that. So how does it come together? In the first place, now I'm going to introduce the audience-aware streaming concept that we talk about. We talked about the static way of doing, or the long-term way of planning for codec profiles and codec choice and so on. And from that, we do something which is dynamic and smart, or what we would like to call smart, for OTT deployments, which we call audience-aware streaming. So that means we have an audience-aware encoding, and we have elastic CDNs. And that's based on real-time consumption analytics that may be, so number of clients, the location, the type of clients, available bandwidth, so whatever information we can use for that. So in practice, how does it look like in terms of architecture? That's something which is more or less classical. You've got the encoder, you've got a just-in-time packaging, which also does the origin. You've got the CEN, and you've got a player at the end. And you can see you have the analytics, let's say software which runs, which does the logs, the reports, and everything in a dashboard, what problems are there, and so on. The CMCD data gets back, so the session ID, the bit rate, and the buffer starvation. That's the main things which we use. And what we do out of that is we add here, basically, these two paths here, and the green ones. Basically, the analytics, so what we call a pilot, which was supposed just to report, basically, and steer the CDN, now is a real orchestrator. It orchestrates, basically, the encoder behavior, configuration, just-in-time packaging also as well, and the CDN altogether. So you have an end-to-end optimization. So just now a couple of examples of applications and how we can use that, what we have identified. So one is the CPU encoding optimization. What you see here as a graphics, it's a curve, it's maybe a bit complex, but all you have to know is that on the vertical axis, you've got a quality, a measure for the quality, and then you've got a bit rate. And what we could show is that for given content, if you add on additional cores, additional CPU cores, with that you can drive the efficiency. You can have a higher efficiency in the compression. So with that, if you have a server with a number of cores, 96 cores for instance, well, if you allocate differently the cores, basically you have a different efficiency for given content. And that's how about to show that. So we have on the left side the classical case. So you've got sports, documentary. So we do it here, we show it with 2 channels. But imagine if you would do this with 200 channels, for instance, for a project, that would be really interesting. So you have sports, documentary, equal audience, no difference between the people. So in that case, you encode both at the same quality. But now what suddenly starts is that people are all going and moving and watching soccer. Or dining, maybe, as we heard this morning. And then, in that case, we increase the number of cores, of CPU cores, and we decrease the number of CPU cores for the documentary. And what happens in that case, we keep the quality constant, so we don't change that. But for the sports, basically, we have the same quality with a lower data rate. Or we could also have, if you want, the same data rate, but a better quality, because we improved the CPU cores. And that's how we can steer it. So I try to put in yellow always some concrete examples so that you can figure out what type of figures we're looking at. So I'm not talking about epsilon nothing. So here, let's say a reasonable value we have is bandwidth of 10 to 15%. Of course, there's a scenario behind this, but this is what we have identified. So in practice, or if you look at the dashboard, this is how it would look like. You have a number of active sessions, so that's where the CMCD kicks in. And you know that you have about the same, so you have no differences. As you can see, the bit rate is the same, so that's the red one on the right. And then, okay, so that's all equal, that's the classical case. Now you change that, and you have more sports audience. That's what you see here on the left-hand side, the sports is increasing. And then you can see here the documentary has a higher bit rate, so less cores, and the sports has a lower data rate and more cores, more efficiency. And that's how you can earn some gain bandwidth, basically, because the overall total bit rate that you need is lower. That's how you can control and steer it. Again, we do it just here for 2 channels, but if you do it for many channels, the classical broadcaster would tell you that this is a kind of statistical multiplexing, for those who know, which are maybe also a bit older like me. So that's a classical case. So now I'm going to come to another application, which is the ladder representation optimization. And this has also many of these sub-use cases. So one is the ladder, so the number of ladders and codec profiles. So typically, for instance, if you look at Apple, they've got recommendation on what type of ladders they recommend, what you deliver. Sometimes you've got an experienced engineer which tells you, okay, this ladder is very good, this codec profile is good, so we take this one. We have this experience based on the logs and so on. That's typically the kind of thing that you can retrieve and find out. But what we can do here is basically do something very dynamic. We look at who is consuming what, and how many people are consuming, and basically we can remove some of the ladders. So the unused ladders, if the connection is very good, then we remove the lower ladders. And all this goes to benefit because it goes back in the CPU cores, which can be allocated, and in which case you can be more efficient. And that's how you can do it. So for Dash, for instance, typically you could use a new period. For LHLS, there are also techniques that you can do. But basically, this is how it works. And well, you have the CPU resource optimization, you need less traffic, obviously, and you have a better quality of experience because the remaining ladders, they can be still advertised at 4.5 megabits per second, but in reality, you go down because you have more CPU efficiency. So you can better match, basically, the actual consumption scenario for the different clients. Obviously, if you have 1 million different clients, then there's a way you need to meet your choice. So you cannot just meet perfectly what every client wants, but there is still optimization there. So another example is the codec. So the codec dilemma always is, when I'm going to introduce a codec, and as you can hear, it's 70%. I think a few years ago, it's more than 98% was still in H.264. And we have new codecs, which are more efficient. So what we can do here also, we can dynamically start and stop the encoding of AV1, for instance, VVC, or HEVC, because HEVC is also a topic where some customers now come to us. Again, HEVC is 10 years old, but there has been a lot of issues, let's say, and these kind of issues also, when do I introduce a new codec? And this is also an example of scenarios we have. So we have, for 500K viewers, over 30 days, I think, if you have 50% HEVC capable clients, then we calculated $800K savings. Of course, there's a scenario behind this. With less 100K viewers, 20% HEVC support, $633 kilo dollars. So basically, that's the thing. You don't have to make a choice on long term. You can just have these codecs whenever you're ready, whenever you have some savings. And basically, that's also what is done in practice. You can define business rules. You can decide, okay, for 100K viewers which support HEVC and which watch for 2 minutes, I'm going to switch over the HEVC. What happens in that case? You have a limited infrastructure. So that means that you take off some of the CPU cores that you used to do for H.264. So your H.264 is maybe less efficient, but your HEVC gives you a gain overall. So the whole thing has to be looked into a dynamic way of encoding, basically. Another example is for the ads. So if you know who's consuming what in terms of the ads from the CDN point of view, then you're able to encode and to deliver the formats and select basically the ads in the right format from the ad pool. That gives you some additional efficiency. You don't have to blindly encode and transcode everything and deliver and hold ready depending on which ad it's going to be. So that's one of the things also which is also quite interesting to look at. Another example is this one is, I must admit, is a bit more complicated. So I'm bringing this with the grain. So there's a lot of topic about how do you preserve grain. And if you take a private soldier, Ryan, I think it's in English, there's a lot of grain, artistic intent. If you looked at the Netflix series, they have also a lot of grain. Of course, if you do news, if you're a news channel, you don't care. Sports, obviously not. So the point with grain also is that if you want to preserve grain, you have to raise a lot your bit rate. Sometimes 3 times, sometimes twice. So on average, you could say 50%. You need to double the bit rate if you want to preserve the grain. The easiest, you remove it completely. And that's also what you could do, for instance, with AV1. It's got film grain synthesis, where you remove it completely, so you save a lot, and then this is regenerated on the device side, which is heavily, well, at least there's a lot of interest behind this. So we did a small exercise, but also, of course, as I said, if you have a full program with entertainment, with shows, with news, and so on, it would be wrong to say to you, hey, buy a new encoder with AV1 all the time with FGS, because it's going to save you. Because, of course, just a small part, maybe, of the programming is just drama, which is suitable for film grain synthesis. So again, we come to the dynamic way of looking at these things. And that's basically what we also showed at SMT. So a way that you can basically dynamically adjust the grain that you want to leave in. So depending on the audience, if you have a large audience which doesn't support FGS, you can leave all the grain in. If you decide that you want to limit your traffic because you have a big sports program coming up and you have a limitation on the CN, then you can also remove a lot of grain. So you will save a lot of bandwidth. You put the rest to the grain. So here's an example, a very simple example I have. It's the case where you completely remove the grain. So you remove completely the grain, and what types of cost savings do you have? So 25% AV1 capable devices, which can generate FGS, you remove completely the grain, you got 10% of the grain programming, you save only 2%. But again, it's 10%, which is only suitable of the overall program. 18%, it's 4% cost savings. If you have more devices, AV1, so I think AV1 is more at 25% and 50% currently, but it's increasing rapidly, then you would have 4% cost savings or 8% cost savings, depending on the programming. If you have a movie channel and you have grain all the time, then happy days, of course, you have much more savings, obviously. Yeah, so I'm already at my conclusion. So we've seen a number of things that can be optimized, degrees can be optimized, and we also are using also this for increasing the number of use cases of applications. We could use that. So we can use CMCD with audience-aware streaming. So encoding efficiency, that's about the cores. The codec profiles, how you select the codecs or how you can increase the number of codec profiles to have the best quality and the lowest delivery costs. The codecs, when do you want to choose the codecs? And that's increasingly a problem. As I said, there are many codecs coming. There's also the successor now of AV1, the successor of VVC coming up. The grain can be adjusted dynamically, and the ads encoding. So at the end, it makes decision-making for somebody who has the hard decisions to say, I'm going to use these profiles, I'm going to introduce this codec. It makes it less dramatic. So if you got it wrong, you still have this flexibility and this dynamicity, so it's less dramatic. And of course, we talked about this morning, delivery cost savings also often means energy savings. So that we should also never forget. Yeah, and just as an outlook, the question here is, I've shown many elements. So interesting is going to be, if you combine all it together, how much is that going to bring? I've got an idea, I could gamble on it, but I'm not going to share the results. But it's going to be at least interesting to see where it all fits together. Dynamicity can be brought to new applications. We hear a lot about personalized rendering. So if you have some preferences, how you want to have format, how you want to have graphics and things like that, basically you can also dynamically encode or not encode depending on who has these preferences. And accessibility. So there's a whole lot of applications you can do in terms of rendering, or how you want to render. We heard this morning about subtitles, sign language, and things like that. How you can just dynamically, of course, obviously here we're not talking about necessarily about business, but we talk about use, about somebody who's needing particular rendering. So that's also kind of new applications we could look into. Yeah, and the next thing, and that's the second time I'm talking about it, it's artificial intelligence. Once you can model everything here, yeah, exactly, thumbs up. Once you can basically boost the pilot with artificial intelligence and modeling basically the whole consumption, the whole explanation, and define these rules automatically, because at the end, this must be also human steerable, then in that case, it becomes really interesting, and there are so many degrees. The challenge with it is, of course, is that we still want to leave the people which are operating this in control. So we don't want to take the decision, okay, we're going to remove the grain here, we're going to put a new codec there, and no one knows at the end what happens. So there's a middle ground to find here, and this is also what we're also trying to practice here. Thank you.